Hello friends, so today we will see how to derive the equation of motion of a damped free vibration. Thus far we were looking at undamped vibration where only spring was there or a mass spring system was there. Now we will look at the effect of damping effect on free vibrations. So consider a system here in which the mass is connected to C, that is a damper, and C is known as damping coefficient. Like the stiffness of spring K, for a damper there is a constant value associated with it. So K is our spring constant or stiffness, and we know its unit is Newton per meter, and C is known as damping coefficient, and it is defined as damping force divided by unit velocity. That means effect of damping is given by a damping coefficient, which is damping force per unit velocity. That means how much damping force is applied for a unit velocity movement of the mass. So we know damping is given to absorb the vibration. So in a free hanging system or a spring mass systems, compared to this one, will have more vibration because here there is this damping, and damping can be associated with uh, shock absorbers of vehicles or springs uh, in vehicles. All of those carry the same function as damping, that is to absorb vibration and reduce vibration or stress in the material. So to derive the equation of motion, let's considering the free body diagram of this mass. So there is a mass here, and due to this spring, there will be a spring force that will be equal to K times X, and there will be a damping force. So we know C is equal to the damping force divided by unit velocity. So damping force will be unit velocity times C. Cos multiplying C with unit velocity will get damping force. So velocity, if displacement is given as x, then velocity will be first derivative of displacement x, that we represent it as x dot. So damping force will be C x dot. So this is a free body diagram of mass. There will be a spring force K times displacement, and there will be a damping force, that is damping coefficient times unit velocity. So according to Newton's second law, we know total force contained in a system is equal to mass times acceleration, and we can write acceleration as second derivative of displacement x. So total masses acting on the system is minus kx plus minus of cx dot is equal to mass times acceleration. So simply it is taken as negative because it will be acting against the direction of displacement. So we can reduce this equation as mx double dot plus k x plus, okay, we can write it in the specified order. So let's write c x double dot plus kx is equal to 0. So this is a differential equation. If you can write in the form of differential equation, d square x by dt square plus c times, okay, that is c times x dot, so dx by dt plus kx is equal to 0. So to solve this equation, we will use an auxiliary equation method by which we substitute x is equal to e raised to st, where s is a constant and t is time. This is the auxiliary equation method. So if x is equal to e raised to st implies x dot will be equal to s times e raised to st. So the differential of e raised to st is e raised to st times s. And also x double dot will be equal to s times e raised to st and again an s. So that will be s square times e raised to st. So substituting this back into the equation, substituting these values back into this differential equation, we will get m times s square e raised to st plus c times s e raised to st plus k times e raised to st is equal to 0. Taking e raised to st as common, we will get m s square plus cs plus k is equal to 0. So this is actually in the form of a quadratic equation with s as the variable. So using quadratic formula, we will get two values for s as s1 s2 equal to minus b plus or minus root of b square minus 4ac over 2a. So that will be c here. So minus c plus or minus root of c square minus 4a. A is m here, m and c is k. Minus 4ac divided by 2 times m. That is 2 times a. So that will be the equation, and we can take that, split up the denominator for both the numerators. So minus c over 2m plus or minus, and take this 2m into the square root, we will get 4m square. So c square minus 4mk over 2m. So this can be rewritten as, no, not 2m, so we're taking it inside the square root, it will be 4m square. 4m square. And again splitting up the denominator inside the radical. So c by 2m plus or minus root of c square over 4m square minus 4mk over 4m square. So we can cancel out and we can simplify it into s1 comma s2, that are two roots of the equation, as minus c over 2m plus or minus root of c square by 4m square minus k over m. 4 and 4 will get cancelled, m square and m will get cancelled. So k over m. So substituting an equation, that is c over m is equal to 2 omega, so 2 epsilon omega n, where omega n is the natural frequency and epsilon is known as, this is an equation you can use for numericals. So this is an important equation. There is no derivation for this equation covering in your syllabus. So I am skipping the derivation of that equation. So that epsilon is known as damping factor or damping ratio. Damping factor or damping ratio. Both are the same names of that equation. Epsilon, damping ratio, c is damping coefficient, omega n is, we know omega n is nothing but angular velocity corresponding to natural frequency. So substituting this c by m is equal to 2 epsilon omega in this equation. So c by 2m will be 2 epsilon omega n. C square by 4m square will be 2 epsilon omega n whole square, and we can keep km. So that equation becomes s1 comma s2 is equal to omega n into epsilon minus epsilon times omega n, because c over 2m will be, it is today epsilon times omega n. So epsilon omega n plus or minus root of epsilon square omega n square, and we know omega n is equal to root of k over m. So k by m will be equal to omega n square. So substituting that, omega n square, so we can finally get s1 comma s2, that are the roots of that equation, as omega n is common, so I'm taking omega n, and inside what will be left with minus epsilon plus or minus root of epsilon square minus 1. This is an important equation for solving numericals, and also to define what is damping, over damping and under damping conditions. So this is the part of the solution of free damped vibration, and this equation represents equation of motion of damped free vibration. That is the equation of motion of damped free vibration. So that equation is important. And if c is equal to 0, that equation becomes mx double dot plus kx is equal to 0, which we have learned for undamped free vibration. And solving that equation, you will get this equation, and this c over m is equal to 2 epsilon omega n is another equation that is to be used for numericals. And finally solving, we will get s1 comma s2, that is roots of that equation as omega n minus epsilon plus or minus root of epsilon square minus 1. So we will continue with this, as what are the conditions of over damping, under damping and critically damping conditions. So now we will continue with the damped free vibration. We have solved the equation for damped free vibration, and we got the square roots as, or the roots of quadratic equation as omega n common to minus epsilon plus or minus root of epsilon square minus 1. So depending upon this epsilon value, which is the damping factor, we call it damping factor or damping ratio, because that determines the effectiveness of damping. So three conditions are there. First one is over damped condition or over damping. You can write over damping or over damped condition. So I will be just writing over damping. That is when this damping factor is greater than 1. So if you put in that equation, both S1 and S2 are the roots of quadratic equation. So over damping gives you real distinct roots for the quadratic equation that we formed out of the equation of motion. So S1 and S2 will be distinct and real. And over damping, as the name suggests, that means damping is given in excess to the required. So what happens is the vibration, if you draw the vibration diagram, this is important, you should only explain over damping is this equation and this symbol diagram. You can explain over damping, and for examinations you will get full marks for just explaining this over damping with this diagram. So over damping, in the case of over damping, let's x-axis be time and y-axis be displacement. So since it is over damping, that means damping is given in excess of the required. That means it will have a peak vibration, and as soon as the damping takes its effects, the vibration dies out. Thus, this is over damping. That means vibration is not reducing gradually. Instead, it is just decreasing steadily. So that is how the over damping condition is. Now let's see under damping. Second one is that exactly opposite, that is under damping. That means damping is not necessary. Or in over damping it was in excess. In under damping it is not necessary to the actual vibrations to be damped. So here the damping factor will be less than 1. Then here the cases of the quadratic equations are roots are imaginary. So if you put it in the equation, we can see S1 comma S2 is equal to omega n plus or minus, sorry, omega n minus of epsilon plus or minus root of omega square minus 1 is our equation. And if omega, this epsilon is negative or epsilon is less than 0, this becomes omega n, and negative epsilon will make it positive, and I am not going to put it epsilon, and we will have an I square term here. I is the imaginary number, I square times or you can, if you don't know how the I square came, then we can write it as negative of 1 minus epsilon square. So we know root of negative 1 is I is root of negative 1 and I square is negative 1. If you remember the complex numbers, you know I is equal to root of negative 1 and I square is negative 1. So you can apply that here. So omega n minus epsilon plus or minus root of, instead of negative 1 I am going to put I square and 1 minus epsilon. Sorry, epsilon square. So you will get S1 comma S2 as omega n plus or minus epsilon plus or minus, okay, omega n plus or epsilon plus or minus I times root of 1 minus omega square. So there is a specific term attached to this that we will discuss later. So this is the equation for an underdamped condition. And if you put it in general equation, that is x is equal to e raised to st, we got x is equal to e raised to st as our general equation. If you put it, then you will get a times e raised to negative epsilon omega n t sine omega dt. You don't have to explain this in the exam or in the derivation is not required for this one, so I am skipping that derivation, and you can only write till here. This is not actually required. I'm just giving it to you, and I am giving it to you because we need something called omega d for our numericals. So omega d is nothing but 1 minus epsilon square root times omega n. That is this term, omega n times the square root term, that is known as omega d. And that omega d you should remember for solving numericals, and omega d is nothing but, as the name suggests, angular velocity of damping or damping velocity. It is better to call it as damping velocity. Damping velocity or angular velocity associated with damping velocity. And we were discussing under damping, that means the damping is not necessary to absorb the damping. So what will happen is, if you draw time with respect to displacement in under damping conditions, if you draw a mean line here, or let's say negative x, if the vibration is occurring, then it will start at a peak, then it will go on and it will not reduce gradually, whereas it should have been reducing gradually to 0. It will not reduce because the damping is not sufficient, so it will go on like that. It should have been reduced by, if you are traveling by a vehicle and if your vibrations keep happening to you like this wave, that is, it is reducing but not reducing sufficiently enough, then it will be dangerous. So this is under damping, that means damping is not sufficient. So this is under damping. And now we will see third one, that is critical damping. In critical damping, epsilon will be equal to 1. And the critical damping means damping is optimal. It is not more than needed, it is not less than required. So in critical damping, what happens is, you will not get a sinusoidal wave like thing, but whereas if you draw a time versus displacement diagram here, you will be having a vibration, but it will be gradually reducing it to zero. Not like over damping. Over damping, you get sudden absorption of vibration. So here it will be gradually you will be releasing it to zero. This is known as critical damping. So let's just review what we have learned. In over damping conditions, damping is more than sufficient. Sorry, more than sufficient. So we can just redraw it so that we can avoid confusion with critical damping. So it will just reduce it to zero in sudden time. So because damping is over. So if you are going by a vehicle and if your condition shock absorber, so your springs are over damped condition, then what will happen is when you get into a pothole, you will get a sudden vibration and then suddenly that vibration will be gone. That is not a pleasant effect on the passengers. And second one is under damping. That means you are getting a continuous vibration without ever reducing it to zero. So you will be going like in a pothole, and the effect of that pothole will be for more than half a kilometer. So you will be vibrating continuously because your damping is not sufficient to absorb. Critical damping means you will be readily absorbed of you would not be readily absorbed of vibration, nor you would have to bear it for long time. So it will be a gradual decrease of vibration to zero. That will be a pleasant effect on human comfort conditions. So this is the three cases of damping according to the damping factor. So two equation you should be careful. That is first one is this equation for damped velocity. That is 1 minus epsilon square root times omega n. So if you got natural frequency and its angular frequency associated with natural frequency as well as damping factor, you can find damping velocity. This is required for numerical. So we will continue with this damped free vibrations. So let's now discuss an important term in vibration, that is logarithmic decrement, and it is represented by a delta d is its notation or representation. So delta d, that is its representation, and it is defined as natural logarithm of ratio of two successive amplitudes. So that means if we consider a condition, let's consider a vibrating condition in which the amplitude is changing with respect to time. So if you can remember the earlier topic, this is a classic representation of an underdamped condition where damping is not sufficient, so your continuously goes on vibrating without with only a marginal decrease in amplitudes. So considering this, let x be in the vertical axis and t be in the time is in the horizontal axis. So each of this from top to top you will get a time period. So you should draw it as equal time periods. I have just made a small mistake where which I have last time period looks a little smaller, but all time periods should be same. So from each maximum points, if you measure, there will be a time periods. So that is represented by TP, and also the height of each one is given as amplitude. So for first time period it is x1, and next time period is x2, x3, and for the initial condition it is x0. So x0, x1, x2, x3 are amplitudes. So x0, x1, x2, x3, and it goes on are our successive amplitudes. Amplitude is nothing but the maximum displacement. So according to this definition, that is a logarithm decrement is defined as natural logarithm of ratio of two successive amplitudes. We can write sigma d, that is logarithm decrement. This is an important parameter for numericals. Two successive, that means it can be x0 by x1, or it can be log of x1 by x2. Similarly, it can be equal to log of x2 by x3. Similar to that, it can go on. So we know for underdamping condition, for underdamping condition, we have defined the equation where sigma is less than 1. We will get a condition x is equal to a to the power of minus sigma e minus sigma nt times sine of omega d into t, omega suffix d into t. This is the condition for underdamping. You are not required to study the derivation part of this one. I will post a separate video for the derivation. We have just mentioned it in the previous part of this video. So omega into t. So when t is equal to t1, it gives x is equal to x1. So we can write x1 is equal to a times e to the power of negative epsilon omega n t1 times sine of omega d t1. Similarly, if you can go for x2, we will get for t is equal to t2, x will be equal to x2, and x2 will be equal to a times e times, so e to the power of omega n t2 sine omega d into t2. So t2. T2. So we know logarithmic decrement is ratio of two amplitudes, natural logarithm of ratio of two amplitudes, taking two amplitudes, let's say x1 and x2 as two successive amplitudes. So if you divide them, then you will get a times e to the power of negative epsilon omega n t1 sine of omega d into t1 over a times to the power of epsilon and omega n t2 sine of omega d t2. So let's call the t2 t2. So if you can simplify that, you will get e to the power of minus epsilon omega n t1 t2, taking t1 and t2 as very small intervals, sign will be same. So equate taking changes in sign function as very negligible for a small interval of time. So we will cancel sign and a is cancelled. So we will get that equation, that is e to the power of negative sign negative epsilon omega n t1 divided by negative e to the power of negative epsilon omega n t2. So we can again simplify it as using the powers as subtraction, e to the power of negative epsilon omega n common t1 minus t2, because we can take the negative power of the denominator as the numerator. So we know time period is equal to t1 minus t2. So we can call it as tp. So we will get x1 by x2 equal to e to the power of negative epsilon omega n tp. So we get our equation for logarithm decrement as natural log of time period. We can take it as t2 minus t1. Sorry, I made a mistake there. So time period is t2 minus t1, that is equal to Tp. So here it is T1 minus T2. That implies T1 minus T2 is equal to negative Tp. So putting it there, so negative and negative becomes positive. So it will be e to the power of epsilon. The negative will be cancelled by multiplication omega n Tp. So taking natural logarithm of x1 by x2 as our logarithm decrement, you will get logarithm decrement as log of e to the power of epsilon omega n time period. This is the equation we will be using to find logarithmic decrement. This is an important equation for your, and you know logarithm and exponents are inverses of each other, so we can cancel out logarithm and exponents and we will get logarithm decrement is equal to omega n Tp. So this is the equation we use for numericals. You can unbox that last one rather than the first one because we can reduce it to a simpler form. So we'll get sigma d is equal to log e to the power of omega n Tp. Since logarithm and exponents are natural logarithm and exponents are inverses of each other, that will cancel out. So this is our equation for logarithmic decrement. And we can substitute Tp, our time period, as 2 pi by omega, and in this case it is omega of damping, so omega d. If you substitute it in that, that you will get as, and also we know omega d, that is damping velocity, is equal to 1 minus epsilon square times omega n. We have derived it earlier, so we will get, substituting this Tp is equal to 2 pi by omega d and omega d as this one, so that will keep Tp is equal to 2 pi times root of 1 minus epsilon square times omega n. So substituting it, you will get sigma d. Let's just move that a little ahead. So substituting it into the equation, we will get, substituting this into this one, you will get logarithm decrement delta d is equal to epsilon times omega n Tp over, so Tp can be substituted for 2 pi times 1 over 1 minus epsilon square inside square root omega n. So omega n will get cancelled. So simply you will get logarithm decrement is equal to epsilon times 2 pi. So I am writing it as 2 pi epsilon, for is 2 pi epsilon over root of 1 minus epsilon square. This is also another equation you can use for logarithm decrement. This can be this equation can be used when you know omega n and time period. This equation can be used when you know only damping factor. Both are used for finding logarithmic decrements. This is used when we know either natural frequency or angular velocity of natural frequency and time period and damping factor. And this can be used when only damping factor is known. This is used basically to find damping factor from logarithm decrement and these two values. So these are the two kind of equations for logarithmic decrement. This is important for finding out or solving the numericals. So we will see what are the formulas required for solving the numericals in brief. So we have covered the theory portion of damped Fourier operations. So in order to solve the numerical associated with this, we should be having some formulas that we have already discussed. So just reviewing the formulas that we have already discussed and derived. Formulas for damped free vibrations. First one is equation of motion. equation of motion for damped free vibration, that is mx double dot plus cx dot plus kx is equal to 0. If C is absent, then it becomes undamped vibration. If C is there, that is damped vibration. Cx Cx dot is nothing but damping force. Mx double dot is nothing but inertia force, and Kx is spring force. So sum of all forces equal to 0 is our equation of motion. So, and in this lot of equations we need, one of the equations we require for solving is the one we have already learned, omega n is equal to root of k by m, or frequency of natural vibration Fn is equal to 1 by 2 pi omega, that is 1 by 2 pi root of k by m. These two equations are necessary for entire vibrations chapter. And second one is, sorry, third one in the equation you can use is C by m is equal to 2 times epsilon times omega n. This is an important equation for solving damped vibration. C is damping coefficient, m is mass, epsilon is damping factor. Just please be careful about not interchanging both. C is damping, okay, C is damping coefficient. C is nothing but damping coefficient, whereas epsilon is either damping ratio or damping factor. Both are same epsilon. And omega n you know as angular velocity associated with natural frequency. That is one equation. And next equation you require is the one we derived last, that is logarithmic decrement delta d 2 pi epsilon over root of 1 minus epsilon square. So epsilon we can get from this equation. If you know C, m and omega n, you can get epsilon from this equation. Put that epsilon in here and you can find logarithm decrement. And logarithm decrement can also be found out as log of any two successive amplitudes. So let n be a amplitude and next amplitude be xn plus 1. That is also used. That is the definition of logarithm decrement. And also you can use another formula, that is logarithm decrement is equal to 1 over n log of initial amplitude divided by final amplitude, where n is equal to number of oscillations. N is equal to number of oscillations. Or now you can also call number of cycles of operation. So that is one thing. And finally, one more equation you require for solving numerical equation is critical damping coefficient, that is given as Cc. C is our damping coefficient, and in critical condition is known as critical damping coefficient. That is when we know for critical damping omega is epsilon is equal to 1. So if you put in that equation in here, epsilon equal to 1 in this equation, you will get critical damping condition. That is C is equal to 2 times epsilon omega n. That we can get from, we know C by m is equal to 2 epsilon omega n. So omega equal to 1, that is critical condition. That means C is equal to Cc. So if you put C by m is equal to 2 times omega n, you will get Cc is equal to, that means Cc is equal to 2 omega n m. Okay, here it is not epsilon, it is omega, it is m, 2m omega n. And we know omega n is nothing but root of k over m. So if you can put in that equation 2 times m times root of k over m, it will be deducted. M and root m will get cancelled and we will get C is equal to 2 times root of km. This is also one of the equations. This is also one of the equations. And another thing is damping ratio can be found out by epsilon can be found out by ratio of C over Cc. So these are all the equations you require for solving damped vibration problems. Questions will be straightforward. Only thing you should be careful about identifying which are the values given, which is damping coefficient, which is damping ratio, what is spring constant, what is mass given, what is angular frequency, and from that how do you find angular velocity associated with angular frequency. Then finding logarithm decrement. For finding logarithm decrement, you should be aware of this damping factor or damping ratio. You can get damping ratio as well as critical damping. So you'll be asked a numerical in which you have to find out all these values straightforward. So you can solve it. So this is all the theory that is containing in free damped vibrations. Thank you.